Probably you will hear a lot of that structural angle in my presentation. On top of being the head of the national delegation, I'm also a member of the FIB Presidium, and I have been co-responsible for a preparation of the Model Code 2020 that has been officially released to public 2 weeks ago. And now I am also coordinating a task group under the special activity group Sustainability. And it's always excited to be second speaker, because then you ask yourself what has already been said of what I was going to say. And so there will be a part of a repetition, but I hope there will be also a complementarity. And I will focus on built environment, and I will focus on concrete. One of the products, after drinking water, I believe the most produced product in the world, not responsible for 73% of the environmental impact, but pretty much in the focus of attention that goes into improvement of sustainability in built environment. This is what I will be talking about. I want to tell you something about the number of the topics that are a kind of stepping stone in creating solution. And a part of that will be into innovation, and a large part of that will be into communication, how we talk with each other, do we understand each other, and are we going in the same direction? And in the end, how can we amplify impact of what we are doing? What is the role of standardization, in particular in mainstreaming, upscaling the things that we are doing, because only by upscaling we really can make a change. Well, sustainability everybody knows, but let's repeat it once again. It's about sustainable development. It's about something that we can continue to do over years to come. It means that we need to look from the broader perspective. Economic perspective is also a very important perspective. We can have perfect solutions, but if we cannot afford ourselves to implement this, this is just impossible to succeed. And there is also this aspect of societal needs. Societal well-being is more than environmental impact only. There is security, there are needs for aesthetics. There are a lot of things in which built environment is an example that we cannot forget this one. So this multidimensionality is important. And why I mentioned it in the beginning already, well, as Liberato said, International Federation for Structural Concrete, we represent largely designers and the one who will construct and maintain the structures. So for us, it's taking care about multiple aspects of the requirements that is compulsory for performing our job. Well, and we have been hearing about sustainability for actually not such a long time. 84, it's when it all started. And if I would be preparing this slide yesterday, and I did 2 days before, then I would need to add one more, 2024. Yesterday, the European Court for Human Rights ruled that having the adequate policy for controlling climate impact is a basic human right. Well, this will change the policy. This will probably influence the policy worldwide, although it only happened on the European scale. It means the attention is increasing. And what we can do is to look at these policies and use them to our benefit. We are, as engineers, as representative of the construction market, one of the important players in a large system in which policies, legislation are also existing. So having contacts and having influence and being aware of that can be our strength. That's also why it's so important to consider also that larger scale of what we are doing and how we are communicating about what are we doing. And it also influences our customers. I mean, that business practices, they function in the reality of the economy. They function in the reality of carbon tax. They function in the reality of the economic constraints. So all these changes will somehow be of the importance for how fast we can move in the right direction. Well, what is the direction to go? What the policies also do, they define targets. And here you see, what probably you already know, a number of the targets that have been already set worldwide, but also in particular on the European scale, and even of the Dutch national scale, to be more specific. This is what I know the best. By 2030, we need to reduce our carbon emissions by 55%. Industry-wise. Well, when you translate it to the concrete sector, it's already a lot. But 2050, we need to be carbon neutral, 100% circular, and we need to build all buildings in net zero. 2050, it's already in a few years. We don't have time to waste. And that's the reason why a number of organizations, communities establish roadmaps. And this is one of the examples that International Federation of Structural Concrete have developed, the targets for reducing environmental impact in concrete construction sector. And I'm talking about structural concrete. This is just a representation of our ambition, this 50% reduction by 2030, 90% reduction, so down to 10% by 2040 and net zero by 2050, total, over the total life cycle. Well, when you discriminate that into the part that is attributed to the cycle, part A, which is the production and manufacturing, you see that our ambition is much more demanding. By 2040, we should become net zero over the part of the A cycle. And now, this slide I also want to use for some other purpose. Quite often we think that that's all, stage A. When we do it, then we are done, yes? Then we did good. Well, although this is just a schematization and representation, there are also other stages that do generate environmental impact. And now this here is largely based on the scale of the infrastructure assets, bridges, viaducts, tunnels, in which under environmental impact in stage B and C, we can also count indirect environmental impact due to traffic restrictions and hinder, and impact caused by the need for rerouting transport means, in particular in urban areas, this will be large. For buildings, it can be different, but nevertheless, there is also that part of the need for improvement that we should not neglect. Well, is it feasible? And sometimes it's good to really be realistic, yes? I mean, like, we can set great targets, but never get there. But who will check that in 2050? I will be retired by then. But this seems really to be realistic. Very simple calculation. What we now do in concrete structures can be improved very fast if we are only able to reduce cement content in cubic meter of concrete, and we know that cement is one of the factors that are very much determining the carbon footprint of concrete by 30%, and we can optimize our design, which is at this moment in general, in routine project, very conservative, and we over-design our structure, then we can already get to 50% of the CO2 emission. It's really not much. We are not talking about zero carbon or low carbon concrete to the extreme that many of you are working on. We are just talking about something that we could do. And think about that. A lot of concrete is being used in the structures that are actually not very demanding in terms of the performance requirements. So let's work where we can work immediately. Let's try to do that already now and go towards that 2030 and 2040, 50 with the large ambitions, because we actually should be able to do it. And now, what are the tools, what are the means, what are the approaches that structural engineers with all the partners involved in that project have to their disposal? We can do a lot, as we already said, in that before use stage A, material production, material and construction process. Reducing environmental impact there is compulsory, and that's evident. What we can also do is we can design and construct to facilitate circular use of the current waste streams. This is also something that we can already mobilize in that stage A. So not only carbon neutrality, but also circularity. You have seen these targets, this policy targets, circularity is also important, just as important probably as using optimally materials. In the long run, we don't want to use that. I have been last year in the conference in Australia, which opened with the great statement from the native owners of the land saying, use what you need, don't use more. I think it's great. We should use what we need, and we should try to use it in the most optimal way. Now, going into stage B, a stage of use, we deal with the built environment in which a lot of assets is already existing. Of course, it is different throughout the world. In the north part, we actually already constructed a lot of the assets, both buildings, infrastructure. In the south, we are still in this trend of increasing the volume of the assets. So this is not generic, but anyway, there is a huge opportunity in improving the way we use our structures and designing for long service life, designing for low in-service maintenance, significantly reducing the impact of stage B. And we can do it both when we design new structure, but we can also do it in case of existing structures by improving our approaches to conservation and use of the structures. And end of life, again, a stage of which we can think, and we can discriminate it in the two situations. Design for use sensible end of life. So how do we build new structures so that we can reuse them, or at least we know what we are going to do at the end of service life? Just to go back to your talk, this is thinking ahead. And another situation is, what do we do with the structures that are already existing, and how we will think before we will decide to decommission this, what we will do with the materials that are coming free after the end of life. With that roadmap of FIB come few stepping stones for creating the solution. The first one, evident, is innovation for carbon neutrality and circularity. We have to have these technologies, yes? I mean, like, this is compulsory. We cannot keep talking. We have to be able to implement new solutions, because the existing solutions definitely have their limitations. Maybe we will get to this 50%, but we want to get carbon neutral, so we need more. The second one is to go into performance-based approaches. Well, the current specification-based approaches have so strong limitations, they will not enable designers to work. They will constrain them in too many ways. And I will soon talk more about what does performance-based mean, because I think here we need to establish a common language. But this is something that is very essential to understand that this is our new way of looking into the objectives of the design, evaluation of performance, and again, to do it both for to do it on all domains of sustainability, for structural, societal, environmental, and economic performance, and thinking about the risks that are involved in our asset structures. I mean, risk is something that we deal with. It's nothing new. It's not that new solutions have risks. Everything has risk. Everything that people are making has a chance of going wrong. And we know how to handle it. Let's embrace it and elevated when we are talking about innovations and improvement. And now we are in Milan, we are in the ahead of the design week, and everybody thinks design is creativity. Well, so is engineering. Engineering is also creativity. It's an art of decision making. So we need to help people to take decisions based on good arguments. This is also one very essential part of the holistic view on sustainability. We are taking decisions that sometimes involve trading offs, sometimes involve compromising economy versus environment. Sustainability, as I said in the beginning, is to being able to endure it for years. Resources are limited. Also, human resources are limited. Financial resources are limited. How can we upscale it with not considering this kind of situations in which the evaluation will involve trade-offs, or at least will involve discussions about trade-offs in which we want to be transparent. Now, as I say, just before, performance-based approach is a must. We all complain about the imitation of current standards that are specification-based, that prescribe how to make things, that limit the freedom of the material producers, designers, contractors, and in the end deliver something that is not exactly what the owners intended to get. Well, why I mentioned the owners and customers? Because these are the ones who know what they must have. They are the ones who set the demands. They are the ones who can articulate their needs, and we have to understand them. There will be a lot of talking about understanding in this presentation, because this is exactly what I think sometimes goes wrong. We don't really listen to each other. We try to sell our solutions without sometimes understanding whether they fit. And now this performance-based needs and requirements can be established on the level of the people, profit, planet, so the overall sustainability, but also in particular on the level of the structural performance. And since this is close to my background, that's probably a part of that talk will be about that structural performance and evaluation. But what do we do when we actually look at the process of creating building assets in general and concrete assets in particular? We should, when we really want to apply performance-based approach, we need to start from the beginning, from recognizing who are actually the players and what kind of role they play in that system. And the first layer of this requirements of the objectives comes from policies, from legislation. There are a lot of demands that society already decided. We accept certain level of human safety, so we accept certain risks. We demand certain level of operational safety for our assets. So quite often they are set by law. We cannot neglect them. We must know them. We must understand that. Actually, we do in that sense what a lot of the things that are, for instance, put in the Eurocodes are already performance-based. This high-level performance requirements need to be decomposed and translated into requirements that are actually technical and relevant for the process of design and engineering. And there is, in that scheme, one very important stage, which is this conceptual design stage or redesign stage in case of existing structures. This is where all the process starts, which is the beginning of the whole creativity. And this is the moment in which it's so important to engage, especially when we talk about innovation, with the players who may have their opinions and their solutions and their ways of handling things. Designers, contractors, material suppliers, and others, all of them can participate, actually should participate in the composition of these performance requirements to create the full set of requirements that we then can evaluate, validate, improve, and so on. Well, what does it mean? Innovation thrives on effective communication. If we forget that step, then we will start again to specify, because this will be this directive way of communication. Please provide me with the material. Here you have material with the strength, do something with it. Now here you have a structure, deal with it. It's not the way we can communicate with each other. So that's the very important part of performance-based design. Do communicate when you establish your requirements, because then this will become the basis for everything that will happen later on. And conceptual design stage is the moment when you do it. And for existing structures, this again, the stage in which we conceptualize the beginning of our assessment and beginning of taking a structure into life cycle management process. And of course, requirements can be revised during the service life, so it's also important to stay flexible and stay alert, because things change in time and we should not forget that. Which brings me to one of the important statements. When I was thinking about this keynote, I was thinking, what actually do I want to say? And actually, I think this is probably the most important. Innovation is a process. No, it's not. It's an ecosystem. You need to innovate together, and only then you can succeed in making your innovation relevant, because then there is something who wants to receive it. There is something who wants to provide it. There is somebody who wants to make it. So as you see, while we are sitting here together, people from the material angle, people from the structural angle, we need to understand that we can only use these sustainable alternatives and capitalize on them if we understand what we actually need. Now, this will be a kind of attempt to establish common language. And maybe it's a technical part, maybe it's too technical for the keynote, but nevertheless, I thought I need it. Well, what do we do, and this is more generic than concrete structures only, and this can be generalized beyond the limit state evaluation and limit state design concepts. But what actually we want to prove by evaluating structural performance is to prove that our resistance is larger than our demands on the resistance. And that can be mechanical resistance, it can be in terms of durability of any other type of performance. Well, I come from that part because many of you do research on material. What do we do? Actually, we tried to understand how that resistance part is being established. And we do actually simulate what reality is. We use models. The models can also be models based on empirics, but we just model reality. And what we have here are the models of materials, and models of materials provide distribution of their properties, but they are bound with certain uncertainty. These are just models, they are schematization, and then we use that as an input in resistance models, because we are talking about structures, so it's not the material that is providing the full resistance. No, materials contribute to provide the resistance of the structural system. So again, we use another type of models to which the material model is an input to establish or approximate the resistance of our system. And the structural resistance models, again, have their uncertainty. And all these uncertainties together, I think, contribute to having this gamma m, this partial factor for material. So it's not only material. There is also this model uncertainty on structural resistance to it. And so uncertainty of material model, uncertainty of resistance model, we need to know them. Once we know them, then we can work with it. That's also the beauty of modeling. Yes, it's so transparent. We only need to have that understanding and this information to be able to proceed. It becomes important when things start to change, because this is nothing new. I mean, this is what we already do for normal traditional solutions. But when we go into new materials, then maybe uncertainty of the material model changes. Maybe the model changes, actually. And the same goes with the resistance models. Are we sure that the same resistance model that we have been using for traditional concrete is still valid for the new type of material, where maybe new mechanisms start to play a role, maybe fracture mechanics becomes different, maybe interaction between reinforcement and steel reinforcing material and concrete is different, maybe ductility is different and starts to play a role. So how good our models are? Well, actually the same happens on the side of the loads. Less relevant, is it less relevant? I don't really know, because when we do design, we have to anticipate about the change in the loads over the life cycle, which is this slide, yes? We don't design for today, we design for the period over which we want to provide that performance. So service period is important, which means that we have to understand how the properties of our resistance will start to change, how the resistance will decrease or increase in time. And the same goes for loads. Well, that's in a few slides, I will need to go back here because this time-dependent phenomena can be different with the new solutions. And if we don't know what it is, then we again amplify the risks of implementing this kind of solution. And it would be very difficult for customers and owners to accept this kind of increased and uncertainties. Probably not correct English, but it's just huge. What do we do? How do we proceed with the process of evaluation of structural performance? Traditionally, we do verification by models. This is the models that we found in codes, national codes, Euro codes, all over the world. Well, we can support verification with testing and monitoring. Testing on the material scale to provide input to the material models, yes, these models. So we can test to improve our material models. We can test to quantify uncertainty of the material models, and the same, we can improve resistance models, and we can quantify uncertainty of the resistance models. This is all the kind of information and benefit when we can get from the testing or from monitoring for the different processes. And of course, we can also go with validation. This is an approach when we will try to establish evidences of the performance. That's actually, again, classic. You will find it in Model Code 2020 as a concept. Now, how can we really implement it in practice? And here I will try to show for only few aspects of the design this needs for research and needs for getting more knowledge. When we talk about structural safety and serviceability, then we have to understand where we stand and where we want to get and what are the limitations of the position in which we are now. Well, what we do when we look at our current models, then we know that they have been established under certain assumptions. And the formulas of the models do not always reveal the background of these models. Yes, we have been spoiled by the fact that everything could be related to the concrete compressive strength. By that, when you look at the model, it seems everything depends on concrete compressive strength. No, that's not true. That's only how we put it in written, yes? So to understand these hidden dependencies as the beginning of establishing, of evaluating adequacy of the models for the other solutions. And I'm now talking in particular about other alternative solutions for concrete. There are also other things that are a bit of implicit. We do assume that there is sufficient ductility in the behavior of our systems. Ductility is a compulsory condition for being able to use models. Stratum-type models, you cannot use them if you are not having enough ductility. And we do use them. Engineers constantly use them because they are very illustrative, they are nice. So do we want to verify explicitly if we meet these assumptions? Or do we have to say certain models cannot be used unless you do verify it? How to handle that? There are also other mechanisms that are not accounted for by the resistance models and current formulas for the resistance models. So this understanding is also very important. And this is a kind of illustration of that process. Yes, when we talk about shear, a classic, it's not only what you see on that figure. It's not only that failure. It's aggregate interlock, it's double action, it's a fracture of concrete. There are a lot of mechanisms involved, and we need to, if we want really to improve that part of structural design, we need to understand how they are being developed in the combination of new materials and alternatives. And this brings us back to this multi-scale character of the process. And here you can see an investigation, DIC, again, that shows distribution of stresses. You can investigate how the fracture of the material, concrete, is developing, if there is any difference, and we could have seen the aggregate interlock experiments here as an alternative for this one. We have been also already able to look at the anchorage between reinforcing bars and concrete in particular. This is a mechanism that is very important for development of force transfer between reinforcement and concrete. So Model Code 2020 provides a way for validation if the current models can be still used for alternative concretes, but actually we want to understand. So this kind of experiments, like this one here, when we test bond under certain conditions, provide us additional information. And then, of course, we want to understand structural behavior. Now, with structural behavior, there is a thing. Experiments are very expensive, and when we don't have results of the full-scale experiments, we may run into problems because a lot of phenomena are size dependent. This here shows the results of the large-scale testing of the University of Ghent with geopolymer concrete compared to the previously shown laboratory testing of the similar materials. And to understand the effect of size effect on the material behavior, of structural behavior, is compulsory because a lot of our structures are large. I mean, usually they are much larger than laboratory specimens. So how to capture that effect in our models? We have to know. Otherwise, again, additional uncertainty, increased risks, and we want to understand our risks. Time behavior, time-dependent phenomena, they play a role on different levels. Yes, this is here creep and shrinkage. We know by experience that a lot of new materials do have creep and shrinkage properties that are different from traditional concrete. There have been investigations that show that creep process does not stabilize, that even after a few years we still have in certain types of materials progressive deformations. Should not be a problem, actually, to deal with it if we knew. The problem is if we assume that it's not the case. And then in our design, we can run into problems with in pre-stress structures with large pre-stress losses, larger than what we have been accounting for. We can run into problems with deformations and cracking if we underestimate forces when designing our minimum reinforcement. So there are a lot of things that designers can deal with if they have that information. And here you see an example of the simulations for recycled aggregate concrete, in which also the creep effects are different from the normal concrete. Well, for instance, in the model code 2020, we have provided models how to deal with this kind of changes in behavior until the certain level of replacement of the aggregate. Of course, if you want, and we want to go higher than 25–30%, if we want to go for 100% replacement, then we would need to have better models that can relate that process to the quality of the aggregates and to the replacement ratio. So a lot of work to be done. Well, again, time-dependent phenomena, but then in domain of degradation. One very important aspect is the long-term stability of material properties. And I will not go back into the slides, but you hopefully still remember when resistance goes down in time and eventually loads go up. And we have to understand how fast. Well, and here I'm not talking about corrosion of reinforcement. I'm talking about stability of the material properties of concrete on which we rely in our structural design. Strength, elasticity, all these things that are the basic input parameters to understand structural behavior. Effect of different phenomena for new materials can be different. And again, it is not a problem as long as we know, because then we don't need to use them at in certain exposure classes. Designers have a lot of tools to play with. You can choose the proper material for proper situation, and optimal material, I should say, for a specific situation. Carbonation, an example here, which is different depending on the combination of the materials in concrete matrix. Well, here example of the testing under sulfide attack. Particular situations, but again, structural designers must rely on the input provided by the material scientists to be able to trust that their input characteristics of material properties they are using in the structural evaluations are correct. And in context of this durability, I just want to mention one thing. We are more and more talking about circularity. So we are thinking about how long can we use our materials. And multiple use of elements in multiple life cycles actually already reality. In a lot of situations, and here are examples from the project in the Netherlands in which we decompose a decommissioned building in order to reuse structural elements, horizontal slabs, walls, staircases in new building systems. This is what we are doing with existing structures. Well, this were done with traditional concrete, but we also need to be able to do that in the future. And what does the climate change mean for that? Do we actually know what is the effect of increased humidity and temperature on the use of these elements? And what if they come from carbonated environment and will be used outside? And the same goes for the new materials. More and more of new structures will be built for reuse, and service life design in context of this circular use is a thing. But again, two examples from Dutch practice. The one here is a new bridge which is being constructed, this highway bridge, full-scale highway bridge, which is being constructed using bridge girders that have been taken from the decommissioned viaduct. So they are already 60 years old, and we want to use them for the next 100. Well, this one is another example. This is a bridge system that has been built for circular use. So this is a new concrete intended to use in multiple life cycle. The design of these elements is done for 200 years. Well, this was still traditional high-performance concrete. But can we do it also with the low-carbon concrete? And how can we circularly use our low-carbon concrete solution in context maybe of also climate change? Now, a few examples, and Liberato, I don't know how much time do I have? Ooh, okay. This will be the very few highlights, only very few practices. Integration of innovation in practice. To some extent, repetition of what you all know, but I only want to have your attention for these examples here, probably. What we have been using in stage A, we already know about, but these are innovations relevant for stage B, low maintenance structures. And this is an example from Japan, where fiber reinforced polymer reinforcement, so FRC reinforcement, has been used in order to eliminate certain degradation risks, but also rapid construction method has been implemented to reduce the, during construction stage, the burdens of traffic restrictions. So a lot of things can be combined with each other. And I think somehow, yes, so this will be the, here, integration of the innovation for stage A before use, where example shown here is the Global Change Institute from Queensland, where the geopolymer concrete has been used for to construct the load-bearing structure. Actually, all these ceiling elements here, floor elements, are done in geopolymer concrete. I believe one of the first building in the world built, fully built in with these materials. But there are a lot of different things to be done. Low-carbon concrete alternatives are one path to go, and here no time to describe which could that be, but also lightweight structures are a way to go. And lightweight structures have also additional benefit that they limit the volume of the material that need to be transported. If we go with the precast structures and we need to transport from the precast factory to the construction stage, well, the energy consumption is somehow related to the mass that we need to transport. So a lot of these benefits start to amplify and combine. And again, rapid construction is one of the ways to go. Circularity, and again, we do not use the materials that we have. The example from Dutch practice that shows that very small percentage of our construction and demolition waste is actually upscaled. A lot goes into foundations. Well, of course, we need foundations for roads, but maybe we can use lower quality materials for that. And use larger part of these materials for our assets. This example, Humboldt University Berlin, recycled aggregate concrete used for the structure successfully and without issues, but also thinking about reuse of fine fractions, ultra-fine fractions. This is a way to mobilize these streams. Designed for deconstruction, and here probably something quite straightforward. We can work with design for disassembly. This will, now what we are now trying to recycle from existing structures are usually monolith connections, very difficult to deconstruct and very difficult to assembly again in a new structure. But if we think ahead, and if we know that the service life of many buildings is 50 years nowadays, and many bridges 60 to 70 years because of functional requirements, then this can really make sense to think about how do we construct and how we also handle the risks. Well, last 3 minutes. Give me 4. Because when we want to increase impact, we need to take next step. Yes, research, best practices, pilots is yet not enough. And there is a lot of work being done, and actually here a piece of all that is available and only collected over the last 2 years, 3 years, because I thought that's just an inspiration, impossible to show you all. There are more and more guidelines and standards being developed in which we try to provide the daily practice support. They are done for different situations. The one above is the Dutch standard that enables use of equivalent performance concept to validate new concrete composition for structural use. This one is the Norwegian standard for use of hollow core slabs. Here you have the first design of geopolymer and alkali activated binder for structural application, the Australian standard. FEBA model code that provides the provisions for recycled aggregate concrete, fiber reinforced concrete, and some first provisions for assessing materials properties, and the French standards also for equivalent performance. A lot of things are happening, and it means that it can be done. We can actually establish specific provisions for the designers to support them in their daily practice. Now, to summarize, yes, and to illustrate with an example that for me is one of the nicest examples that combines all. What may look like a very modern architecture is actually the refurbishing of very old and regular high-rise building in Sydney. In that case, everything has been recycled, and whatever has been added to it was optimized from the point of carbon neutrality. The core of the building is reused. The slabs that were cast to achieve that architectural design have been made with the recycled aggregate, which was actually the product of the demolition of the parts of the structure that became obsolete. And it's beautiful. In the end, it's beautiful. But it took a lot of effort. There has been a willingness from the owners to accept this project. So they took risks because it was innovative, it was highly innovative, and they communicated apparently well enough to have the courage to take these risks. So that communication between the contractor, the designer, the manufacturer of the products that have been used, and the owner was the key to success. So we can make that next steps, provided we do understand each other, and we know that we always dealt with risk, whether it's innovation or not, and that we can do it because we trust in our knowledge. And I think that will be the closing of my presentation.